Okay, so in this video we're going to go over the derivatives of logarithms and exponentials that have a base other than e. So they're very similar to base e. There's just a little extra flair going on in your derivative rules, and hopefully I'll be able to explain that, of why there's extra. Okay, so we already tackled the natural log and e to the x. So that's what you see in this box over here. As far as what's happening. What I'm going to do is talk about what if you have a log base 2 or a log base 10 or whatever. This is what we're going to consider, like, this is the side that's like base A. Okay, so you could have any base that you have going on. Okay, so all you have to do is add this little extra natural log of A. It's a number, it's just a coefficient really. And so we have the same disclaimer that we had in the past, where this is a good derivative where x is greater than 0. So you kind of saw that over here. That same disclaimer is there. And so I'll talk about that if I didn't in the last video. So again, the second versions of the derivative of, the natural log of x, 1 over what's inside, right? It's really 1 over that something. If you have something, other than x, so the derivative of the natural log of u is 1 over u and then chain it. This is really just the chain rule of what was above, with the same disclaimer. The stuff inside that logarithm has to be non-negative, okay? It has to be greater than 0. So there's our base model. Over here, same thing. Here's the same exact idea where I'm going to take a look at the derivative. The derivative of log base A of u is going to be 1 over this, this extra coefficient of natural log of A, natural log of the base, over what was inside, and then you're going to chain it. So same disclaimer that you're going to have. In this case, it's where u is greater than 0. So let's talk about some of the things that we did at the, in our last video where we were talking about base E. We have these great properties that totally work and are great. And so there's nothing special about the natural log. They work for any logarithm of any base. So if you happen to notice, hey, I have log base A of a product, go ahead and break that down into, a summation there. You can break up those logarithms and put a plus sign in the middle. Here I have a quotient, right? X over y. Then break it up into 2 separate logarithms with a subtraction inside. And this last one, if you have log base A of x to a power, notice that power can come in front. That is not a derivative rule, that is a property. So that's an important one to use as well. Using these properties usually makes your derivative go a lot cleaner, a lot faster. Now, I want to sort of address, why do I have this extra, natural log of A in my derivative rule? And it really has to go back to this change of base formula that you learned, I don't know, in pre-calculus or some other fancy algebra class, right? This is a string of equalities here. All of these are the same. This log base 10, that's what's known as your common log. Obviously here, there's your natural log, that's base A. But this works for any base. You can convert any logarithm to a different base if you feel like it. What I'm going to do is just kind of highlight the important set of equality here, I guess, is log base A of x is equal to natural log of x over natural log of a. That's a valid way of sort of, doing a change of base. It's natural log of the inside of the logarithm over the natural log of that base. So this is where I'm really kind of getting at, where does that, why do I have a natural log of a in my derivative rule? It really has to do with the change of base formula. So if I just rewrite what this looks like, right, I could just say, well, it's really a coefficient of 1 over natural log of a, that's one giant number, times the natural log of x. That's what log base A of x is equal to. This is a true statement, right? So if I'm going to get in here and say, oh, I want to do the derivative. I want to do the derivative with respect to x of log base A of x. No problem. I'm going to look over here because that's what log base A of x equals. And I'll take the derivative of this, right? So I can say, well, 1 over natural log of A, that's just a number. It's just a coefficient that just kind of comes along for the ride. And then the derivative of a natural log is 1 over x. And that's what you see up here, on our work here of our notes. And so that's why it's there. So I just wanted to give you a little extra reasoning of why that's happening. Now, what I also wanted to point out is that those little disclaimers up there about, hey, this derivative only works where x is greater than 0, in either of these cases. So what I did here is I'm a nerd, and I graphed a logarithm. In red, I'll just try to color code it correctly. This is the graph of log base 2 of x. And so then I graphed its derivative. So let's write its derivative down, right? That would mean dy dx in this case would be, let's see, 1 over the natural log of 2 times x. That's what the derivative is. Now remember, it's sort of understood. You can just box this up and say, hey, that's my derivative. It's pretty much understood that it's only good for x greater than or equal to, greater than 0, strictly greater than 0, because that's the domain of your original logarithm, right? You can't have a derivative for an x value that's not in the domain of that original function. So really, when I think about the derivative of this log base 2 of x, it's only this little piece. I just want to be really clear about that. So if you have a fancy graphing calculator and you can graph these things, please realize you have to cut that whole left-hand side off of that rational function because it doesn't make sense for this problem. So I just want to be really clear about, why is that? It's because the domain of your logarithm only goes from 0 to infinity exclusive. You can't possibly have a derivative at -2 because there's no graph at -2. So I just wanted to make sure that that was clear. Okay? You don't have to state the little disclaimer over here. I just wanted to point it out. Okay. Now, when I start getting into my derivative work, right, you can go back to your properties. Those are always helpful. I kind of started with a friendly natural log over here. And then we'll get into the logs of different bases. But I'm pushing the issue again where, it's generally a good idea to use properties if you see it and you notice it. So I'm going to do it that way. And we'll talk about a couple of things along the way. So for here, again, I'm not actually taking the derivative. I'm going to use the properties, which would be log of 3 plus the log of x squared. I see that product in there. You're allowed to separate it. I'm actually going to go further with it and say, hey, not only can I do that, I can actually take that power of 2 and dump it in front. I haven't done any calculus work right here. This is all pre-calculus. But now I've gotten it, this big logarithm down to 2 smaller guys. So now I'll come in here and take the derivative and say, the derivative of the natural log of 3, that's just a number. So the derivative of a number is 0. And then I'll write that in, I guess. And then here, that 2 is my coefficient. The derivative of the natural log of x is 1 over x. Now, I'm going to write this down here. Technically, I'll write it and then I'll erase it. Technically, you can write natural log of e. That's the base of the natural log. The base of the natural log of is e. But you know that the natural log of e is 1, so it's unnecessary work. So you could do it. We just don't ever have to, so I'm going to cut it out, okay? But I'm just saying it would work. Okay, so there is a good derivative. My derivative, I'm just going to, let me go back to red here. My derivative here is 2 over x. Got it. Okay. Now, you didn't have to do it that way. You could have, instead of using the properties, you could say I decided I didn't think about those properties. I figured it was easy enough. I'm just going to directly chain it. That's fine too, You could totally work on that and say, okay, well, I have this original equation or function, right? Natural log 3x squared. It wouldn't be horrible if you said, well, I'm just going to take the derivative as it is. I don't think this is terrible. It's 1 over 3x squared. I don't need to write the natural log of e. There's no extra. It's just 1 over what's inside. But I am going to chain it. The derivative of 3x squared is 6x, right? And so I get 6x over 3x squared, and that will reduce down to 2 over x. So either way you think about it, we get the same derivative. So that's wonderful. Now that we're moving on to example 2, this is log base 6. So I'm going to have to show that in my derivative work that I have a log of a different base. And I'll go ahead and do that. I'm going to say I'm going to go with dy dx here. Now, please note that there is no property to address what's going on in that logarithm. There is nothing that talks about sums and differences inside a logarithm. When you go back up to those log properties, you can break up a product, you can break up something with a power, you can break up a quotient. You can't do anything about this. You just have to get in there and take the derivative. And so the derivative is 1 over, I'm going to start with that natural log of 6. It's just a coefficient, but I don't want to forget about it. And really, the derivative of any logarithm is 1 over what was inside, unmessed around with, and then chain it. So I don't know, the derivative of x is 1, and the derivative of -3 is 0. And so that's a good-looking derivative. I don't really even need to have written the 1 down there. I'm just going to rewrite it and move on. This looks great. Okay. Now, when I come to example 3, I want you to realize, like, there is a reason you take Calc 1 first. This is an interesting function for sure, an interesting equation. You've got the function 4x multiplying this log base 3. So you've got a product situation on your hand. Please make sure that you are correctly executing the product rule. You cannot just take the derivative of each leg and slap them together. It doesn't work like that. So I am going to get in here and do the derivative using the product rule. Remember, with the product rule, the order doesn't matter because it's addition. So I usually leave the first function unchanged, and then I come after that, the derivative of the second guy. So that's going to be 1 over natural log of 3, and then what was inside was x squared plus 8, and then I'm going to chain it. And now I'm going to finish out the product rule, which is now taking the derivative of 4x, which is 4, and leaving the log base 3 alone. I already took its derivative, so I don't have to do it again. So that's pretty good. I'm going to, kind of regroup on that first term. It looks a little junky, so I'm going to gather that together and just make the numerator 8x squared. And I don't think I need to get a common denominator, but I will mention something. I think this looks pretty good. I like it. I'll put a little check mark. It looks nice. A lot of math people do not like leaving their answer with a log base 3. We generally prefer natural log. So just as an extra. So I'm actually going to box this up. This is correct. I don't know. It's correct. But if I wanted to, which a lot of people will, you're going to see a different answer potentially, where maybe you're going to see them switch out. Nothing's happening here in the first term. This is just the way that it is. But when I refer to convert to a natural log, I mean this log base 3. Let's convert that. Remember that change of base formula. Log base a of x is the same thing as the natural log of x over the natural log of a. That means it equals the natural log of what was inside over the natural log of 3. So this is an equivalent statement, and you might see that, and I don't want you to be confused by it. Math people are weird, and we like natural logs. So if there's a way to convert it over, we're gonna utilize that. Okay. So here's our last one on this page, dealing with the derivatives of logarithms other than base a. All right, and this one, looks like I forgot to write something in here. You've got the log of 4x over 3 minus x squared. There's no base, so it's understood when there is nothing written here. This is a log base 10. This is a common log, so I'm just going to slide it in there. Why not? Okay, now this is one of those guys that, yes, you can use those properties, and please do. This is a quotient. So before I even start taking the derivative, I'm going to say, well, hey, I can break that into log base 10 of 4x minus log base 10 of 3 minus x squared. I could even keep going, right, and say, let's blow out that first guy. That's log base 10 of 4 plus log base 10 of x. And then I can't do anything to blow out that last guy. That is, so you just 3 minus x squared. Again, there's no property to dealing with a difference like that, 3 minus x squared. So now that I have it rewritten, now I'm going to actually take the derivative. And so I guess I'll switch back to reds. That's what I've been using. And so I'm going to take the derivative of each individual piece. So it looks like I made this function a lot worse, but it's actually more pleasant to take the derivative because, let's be honest, this first term here, log base 10 of 4, That's just a number. I don't know what number it is, nor do I care, because the derivative of a number is 0. So, good. Moving on. Next term, the derivative of log base 10 of x is 1 over natural log of 10. Can't forget about that little coefficient. And then just an x. That was what was inside. And I'll do the same thing on the next guy. Natural log of 10 down there in the denominator. And a 3 minus x squared. And then I have to chain it, so I do have to be careful there. And so I'll just regroup my final answer here. No reason to put a 0 there. I'll just kind of rewrite that second term. And then I'll combine that to a positive 2x. Just with that double negative you see going on. And that is a great looking answer, right? Okay. So that's our work with logarithms. Bases other than e. So let's slide to our next leg of 5.5. Section 5.5 in your textbook is kind of quirky, where they just kind of do both logarithms and exponentials. And so we've already handled in our last set of notes base e. So whether you're thinking about it itself, I think we proved this one. The derivative of e to the x is itself, which is pretty wild. And then remember, the second version is just the chain rule of that first expression. What we're going to tackle today, that's new, is over here, is this here's the new stuff. If you have a to the x, so 4 to the x or 10 to the x or whatever, what's the derivative? Well, the derivative of an exponential is itself. I want you to see that. The derivative of a to the x is a to the x. You just have this extra coefficient flying around. Once again, there it is. It's just a number. And it flies around in both cases, whether you're talking a basic exponential or something more interesting that requires a chain rule. So I know we already proved e to the x. Let's go ahead and prove something without a base e. So just for the sake of argument, let's say we're going to prove the derivative of 4 to the x. So using this rule here, I'll just go ahead and say what it is. Using the rule, it's going to say, well, I'll say dy dx is natural log of 4 times 4 to the x. That's what this property, this derivative rule is trying to tell me. But let's go ahead and actually work with this and guarantee that is what's happening. So I'm going to switch back to purple over here, and I'm just going to take the natural log of both sides of this equation. So I'm going to do natural log of y, natural log of 4 to the x, and that's just, I have an equal sign there. I'm just rewriting it in a weird way. I started with an explicit function of y equals, right? Y was explicitly defined as a function of x. I've now transferred it to an implicit function, implicit equation, where now I don't have y equals. I have natural log of y equals. Now, because I have a natural log over there on the right, I can use that property which says, hey, take that power and dump it in front. Now again, I have an implicitly defined equation now. So right at this moment, I'm going to take the derivative implicitly. So take derivative implicitly. So what does that mean? Well, the derivative of the natural log of y is 1 over y. And then you're going to slap a dy dx on it, because that's what you do with implicit differentiation. Right? Variables don't match. Over here, you have x times a number. Remember that this is a number. So the derivative of x is 1, and then this number just kind of comes along for the ride. That 1 is just the derivative of x. So I'm going to get dy dx by itself here. That means I'm just going to slide the y over. I don't need to write that 1. And so I'm going to replace. Now, technically, this is allowed in implicit differentiation, but we started out with a function that was defined as y as a function of x. I should be able to get my derivative to be the same, to be all in terms of the x variable. So I'm just going to replace y with 4 to the x. And that is the same thing. That's why you have that little extra natural log of 4 in there, right? Multiplication is commutative, doesn't matter what comes first, what comes second. So I just wanted to show that to you, just so it doesn't sound like I'm trying to trick you or anything. So that's one of our new rules for derivatives. So we're going to do some practice, right, with some functions, some equations, take the derivative of. This is a classic question to try to mess with you. You have certainly taken the derivative of x cubed many a time, and then the new part is the exponential base 3. So what I want you to remember is, again, you pass Calc 1, you know that you have to execute the product rule here, and so I'm going to do that. I'm going to say, okay, I'm going to leave the first unchanged. The derivative of 3 to the x is natural log of 3 times 3 to the x. And then I'm going to do the flip side of the product rule, which is the derivative of the first, which would be 3x squared, times that exponential all by itself unchanged. So notice, be careful with your handwriting. Make sure that that second guy looks like 3 raised to the power of x, not 3 times x. If you get lazy and you start getting slanty in your handwriting, bad things can happen. This is a very good derivative. I'm going to be honest, this is great. You're probably going to see, like, you know, if you look in the textbook and stuff, they're probably going to factor out a GCF, so I might as well do it. If you notice in here, I don't know, I'll just kind of mention it. Like there's a 3 to the x, that's part of your GCF. Notice there's x squared here and x cubed there. So we're going to take out a GCF of x squared 3 to the x. What that would leave us with here is an extra x and a natural log of 3. And on the other side of the plus sign, that would only leave us with a 3. So these are both perfectly lovely answers. I just figured I'd show both of them to you. 2 looks pretty terrifying because it's an exponential base 5 with a trig function in it, so that's kind of fun. And we're just going to get right to it. There's no property to deal with here. This is an exponential, not a logarithm. So remember, I guess I want you to realize that the derivative of an exponential is always itself. I'm just going to start with the natural log of 5 because that's the base of the exponential. But I am going to put this exponential function in the derivative. That's how they all work. Now this one's certainly more complex because I don't just have 5 to the x. I have some other function going on here. I have to take the derivative now of the sine of 4x. I have to chain this completely. So the derivative of the sine of something is the cosine of that something, and then you have to multiply by that 4 because that's the derivative of 4x. So this is a three-way chain, as I would call it. This looks lovely. I think my handwriting looks okay. I have a tendency to regroup and put all my coefficients in front, and I usually end with the exponential. Again, so there's no confusion with what's in that exponent. So I would rather it look like that. And if your handwriting is really bad, then you know what saves you? Parentheses everywhere. That could really save you. If you're really worried and nervous about it, then you could write it like that. And that's very, very, very clear. Okay. Let's handle the last 2 questions, which are really interesting and really quirky, and also piggybacks a little bit on the last set of notes that we had worked on. This is problematic for us. Question number 3 is certainly interesting. I have no rule to handle this because I see that x is the base, but in order to use the power rule, I need a number exponent. That's not a number, that's another variable, right? So I don't have any way of doing this. This is not a polynomial. This is not something the power rule could work on, like x squared, right? Where I have a variable base and a number exponent. It's not something that we just talked about, you know, like it's not 2 to the x. It's not a number base and a variable exponent. This is both. This is a variable base and a variable exponent. This is really complicated, and I'm going to have to handle it in a really different way that we've already discussed, actually. Let me actually completely cut that. Cut. So let's tackle this. What I am going to need is something fancier. This is one of those times you're going to say, well, this is a really interesting equation. Let me rewrite it. I'm going to write it y equals x to the 3 over x. This is one of the very few times in your life you're going to say, man, this would be great. If only I had a logarithm in this equation, then I could drop that 3 over x in front, right? So I'm actually going to do this. We're going to handle this via logarithmic differentiation. So that means I am going to introduce that really nice natural log into this equation. Whatever I do to one side, I'd better do to the other. So I've maintained the equality in this statement for sure. What I want to make sure that I can do is that I can get to a good-looking derivative. So what I can do on this right-hand side is use that property of like, hey, you can bring that 3 over x in front. That's legal. That's not a derivative. That's just a property. And then I can sort of get into this. Like, let's take the derivative of this. Now, I'm going to take the derivative implicitly, of course, right? So I'm going to kind of put that over here. I'm taking the derivative implicitly. So the derivative of the natural log of y is 1 over y dy dx. So I finally see a dy dx turn out in my work. Over here, please recognize this is a product. This is 3 over x times ln x. So I'm going to product rule this. I'm going to say, let's leave this alone, 3 over x. The derivative of the natural log of x is 1 over x. I'm going to add to that. Now let's be careful. 3 over x is 3 times x to the negative 1. I'm going to do a little side work here. The derivative of 3 over x, well, what am I going to do? I'm going to bring that power in front and reduce the exponent by 1. I'm just product ruling. Okay, I'm going to regroup. This is 3 over x squared. What do I have over here? This is negative 3 over x squared ln x. And so you want this to get to say dy dx equals, right? So that means I'm just going to pop that y over to the other side. And I'll go back to that statement of like, hey, you know, if your equation was all defined in terms of the x variable, I should be able to get a derivative all defined in terms of the x variable. And I can certainly do that. I'm just going to replace x with what it was defined to be. You even have a common denominator up there. You might as well just throw them together. I mean, you don't have to, but it just happens to work out. There's a good looking derivative. Okay. And I'm going to use the same approach on this next example. So the good thing about all these videos, guys, is you should be pausing them and kind of working on it and then play it and check it and see how it goes. So I would suggest pause the video right now, see if you can handle example 4, and then fire it back up. Okay, so I'm going to slide this up. This is the same crisis. This is a variable base and a variable exponent, and that is something that I'm not going to have a rule. I'm going to have a strategy to approach this. This is going to be that logarithmic differentiation again. So again, I'm going to introduce a log into this equation. I'm going to do so legally. Hold on. Because I'm going to, whatever I do to the one side, I'm going to do to the other. Now the reason I did that is so that I can bring that exponent in front. Notice how quirky this looks. Kind of makes you dizzy a little bit. 2 logarithms over there. Now, I am going to take the derivative implicitly at this step because you have just kind of converted this over. This used to be y explicitly defined as a function of x. It is now implicitly defined. So I'm going to invoke implicit differentiation. And I'm going to product rule. Sometimes it'll be a quotient rule, whatever it turns out to be, right? So I'm going to do first times the derivative of the second plus the derivative of the first times the second unchanged. I think I will regroup. Because I like to. And I want this to say dy dx equals, I'm going to slide that y over. And while this is an equivalent derivative, right? Let's see if I can make that look better. Not so much. I do want to replace the y with a function of x because that would be standard practice. Let me try to write very neat. You can take the derivative of anything It can be awful and terrifying and silly, but any function that is dreamed up, you have a way to handle it. This is the quirkiest one that you have to get really fancy with logarithms, but you can do it. This is very complicated, and you accomplished this goal.